Hello, my name is Brad Erickson. I'm director of the AI Lab. In this video, we cover two sides of a paper. Two sides of a paper reflects the fact that almost every paper has two sides to it, the parts that are very strong about it and the parts of the paper that are not as compelling. No paper is perfect, and we recognize that the publications we have made also have points that are weaker as well as strengths. In this presentation, we present a more entertaining format than a traditional review of a paper in which we have two sides of the paper presented, the strengths and the weaknesses, or the points that are good about the paper and the points where the paper perhaps could be strengthened. In today's debate, we have Mana Moasefi and Poria Rose-Rauk taking the two sides.
There is some variation in labeling schemas, but organizations like the American College of Radiology Data Science Institute has suggested standardized use cases as a starting point to facilitate the proliferation of interoperable labeling schemas, enabling the comparison and analysis of proposed artificial intelligence algorithms. When feasible, this is a great way to handle schema noise, but achieving homogeneity in labeling schemas for all available public datasets, usually in retrospective way, may be impractical and prohibitively expensive task. It's also true that having noise can have a negative impact on our model, but sometimes noise can actually be beneficial. Adding noise to the data can improve generalization by helping the model learn to be more robust and less sensitive to small variations in the input data and prevent overfitting. This is because noise can simulate the variability that is present in real-world data and can force the model to focus on the most important features of the data. As a result, in some cases, adding noise into the training data can help improve the model's performance and make it more effective at handling new and unseen data. Irrespective of the potential benefits and drawbacks of the noise on the trained model, it is crucial to explore the feasibility of eliminating all forms of noise. Additionally, ensuring the accuracy of gold labels poses a challenge in cases where human experts disagree on classification of a pathology due to differences, for example, in terminology. Here I give you an example from the paper. The authors observed different levels of agreements across labels. In chest X-rays, for example, median agreement was high, 0.95 for support devices, and very low, 0.65 for labels such as consolidation and pneumonia. There is a 35% difference in the level of labeling agreement on one of the most common pathologies seen in chest X-rays. So the practical point is that labeling will never be perfect and maybe sometimes quite poor. There has been also much work on the values of automated or semi-automated labeling, which may have a slightly higher error rate, but that may be more than offset by the large gain in the dataset sizes. Given these considerations, it may be prudent to develop models that are capable of effectively handling noise by exploring different approaches, such as adopting different architectures, regularization technique, loss designs, and sample selection, or using some techniques like label smoothing. Additionally, using techniques that can provide indications of uncertain labels and showing us a flag when the model is uncertain offer a more effective alternate.
Developing supervised deep learning models requires a critical first stage of data collection with adequate labeling. The first step in accomplishing this is to provide the labeling schema that will be used for data collection. As an example, consider a deep learning system that may be trained to recognize one or more pathologies on chest radiographs. To do this, the exact pathologies that the model is expected to identify must be defined. The list of pathologies is usually called a labeling schema. Second, each radiograph in the training set should be manually labeled by one or more experts using that schema. Although this seems obvious, both the steps of defining a labeling schema and labeling the data based on that schema are subject to noise and errors. So let me quickly go through the significance of each of these steps and the reasons why we should do our best to minimize errant labels. Let's start by talking about labeling schemas. We are all aware that the ground truth data determines the capabilities of a deep learning model. Given that a deep learning model cannot be expected to execute an infinite number of tasks at the same time, experts often decide on a small set of labels that their ideal model should be able to identify in the data. This decision will affect not only what the trained model is capable of, but also which labels it will miss or ignore when it comes across them in practice. Consider a model for screening chest X-rays. Should this model be educated to recognize only the common disorders, or should it also recognize important but rare pathologies? Should each pathology be labeled independently, or should some disorders be grouped together, for example, maybe under a term like consolidation or neoplastic? These questions may receive varying responses from various researchers, which is how a schema noise is created. A schema noise is by definition created when multiple labels apply different schemas to clinical tasks that users anticipate to be the same. Such noise might have significant practical ramifications. For instance, it is not always possible to compare two models that were trained for the same task but with different labeling schemas. Each model has their own advantages and disadvantages, and perhaps one of them can identify all disorders that the other model can't. While it is unrealistic to expect deep learning models to recognize every possible label, it is the responsibility of domain experts and developers to take into account the deployment context, current workflows, and previously developed schemas before coming up with a new set of labels to train their models on. Even with a carefully designed labeling schema, there are numerous circumstances in which data labels remain noisy and, as a result, expose subsequent models to unforeseen defects. A common example is when multiple experts each label a fraction of the training data. Even with the present labeling schemas, different annotators may assign or omit particular labels from data points based on a variety of criteria. It is well known that different radiologists will be more sensitive or more specific, operating at different points on the ROC curve. That heterogeneity could result in mixed gradient signals to the model during training, thus lowering its performance. Another instance of label noise is when another automated or semi-automated program performs the labeling process. For instance, if a huge collection of medical imaging is labeled by a language model that has analyzed the radiology reports for that imaging data, the labels assigned to some data points may be incorrect due to the errors of that language model. Label noise, regardless of its source, will likely have negative impacts on the model. First and foremost, every model is only as good as its training data. If a model's training data contain a considerable amount of noise, it is likely to have inferior performance. Second, noisy labels could also be present in the test data used to evaluate the model. If the ground truth data against which a model will be tested on are noisy, the model's actual performance may be better or worse than the evaluation findings on the noisy test set. Thus, one cannot rely on these evaluation outcomes. Long story short, it is recommended that researchers do their best to control any source of label noise in their data and to implement an adequate data handling process before proceeding to model development.
So data cleaning is an important component of doing high-quality machine learning and deep learning work. How much data cleaning is really necessary in order to get a good result?
Yeah, I believe that kind of depends on the problem at hand and what kind of expectations we have from our models. Because for some tasks, like for example, building a registry, it's very important to keep the data as clean as possible. The problem that could happen is that if you have a machine learning model that is not almost perfect, probably due to some errors in the labeling, then the registry that is going to be built on top of that is also going to have some sort of errors. And these registries usually are used by a lot of downstream models to come with further machine learning models, and then the kind of error that you had in place for the first data is going to somehow propagate into all downstream models as well. So that's one thing to have in mind. The second thing is that if you're going to let some labels remain in your data, it's always good to have at least a part of your data as a clean test set, so that you can then test your model on that clean test set and see how is your model performance depending on the amount of label you have there and the amount of noise that is still in your labels. So I believe, first, it depends on the task. Second, it's always good to have a very clean test set aside.
Excellent. So if it should be very clean, that kind of raises the question of, should we keep putting effort into it until the data is perfect? Is there ever a case where a little bit of noise is a good thing or at least tolerable?
While noisy labels can negatively affect the performance of a deep learning model, they can also serve as a regularization technique to improve the model's ability to generalize. To understand how noisy labels can affect this model and be used as a regularization technique, it's helpful that we consider this issue as a bias variance trade-off thing in machine learning. In brief, the bias variance trade-off refers to the trade-off between a model's ability to fit the training data, which means that it's low biased, and the ability to generalize, which means the low variance here. Actually, noisy labels can act as a form of regularization to introduce the diversity in the data. So they can be, in this way, helpful. And the other thing, if we want to be more specific, the noise in the labels can introduce a form of stochasticity in the training process. So these are the ways that come to my mind about this, about how this noise can be effective and helpful.
So in both of those questions, there was an assumption that we know exactly what the right answer is and what the label is. That isn't always possible. There are times when we don't have ground truth, that we don't have a way to know what the future will be if it's a predictive. And sometimes experts disagree. Any thoughts on how we can handle the situation where there isn't a clear label?
Yeah. So I guess that's almost always the case with annotating data for AI models. And I can think of three main solutions for that. The first one is coming up with a very clarified, very clear labeling schema. And that is very important because, when you're labeling, when you're annotating some labels for your model, it's not always the case that you face very regular data. A lot of times you are facing that edge cases that happen once in a while, but if they happen, then your annotators could disagree on those. And then, if this kind of noise propagates into your downstream model, it's going to damage your performance a lot. So it's good to have a labeling schema that covers not only the regular cases, but also these rare edge cases. The second solution is that it's always good to have your annotators go through a few of annotations and then come back, join together, and discuss those annotations they did. Because a lot of times you simplify processes in your minds and think that, if I assign, for example, X and Y labels to the data, it's going to be enough. But you go to the data, you start the real labeling and realize that it's not going to be enough. And the third is that, regardless of how good your labeling schema is, there are always cases that your annotators might disagree with each other or might be in doubt about what correct labeling they should assign to those. So in those cases, it's good to have them come together, join together, and specifically have some experts join them as well, and then all together talk about those edge cases and see if they are going to consider them, equally, if they are going to assign equal labels to them, or if they think differently about them. If they can come up with a consensus on those edge cases, then, the labeling schema is going to be acceptable. It might not be perfect. It never is, but at least it is going to be acceptable. It's not going to negatively harm the downstream model.
Adding to what Priya said, I think being consistent in labeling, in producing the labels is something which is a big key for us, because annotators, over time, even annotators grow and they may change their minds. So I think the consistency in this process is also a big important issue.
Yeah.
Great. Thank you, Mana. Thank you, Poria, for all your thoughts on the challenging issue of how we label data with deep learning.
Thank you very much. Thank you.